Good morning, kids. Feel like a proper workout for your rigid bodies? Well, I'll be damned. So am I. Let's cut the jibber jabber and get to it. Well, let's first have a look at what makes these rigid thingamajigs so special. The special properties of rigid bodies are best explained in direct comparison to a real body. Let's have a look at two cylinders. To the left, we have a regular can of soda, and to the right, we have a geometric shape, a cylinder. I'll give you a sec to find out which one of the two is real. Hint, it's the left one. First, let's look at their shared properties. Both bodies have mass, which means that they are inert. In other words, we need to exert a force on both bodies to accelerate them, following Newton's second law, F equals m times a. However, if we exert the same force on both bodies, they will react in different ways. And this is because of the fact that rigid bodies cannot be deformed. This is the most important property of rigid bodies, which has a few other implications that we will take a look at now. What's lying there by the side of the road? Well, it's a crushed can. In fact, it doesn't take a whole lot of force to change the shape of a can. On the other hand, a rigid body can absolutely not be deformed. You can drop an atomic bomb on it, and nothing happens. Spoiler alert, there are no rigid bodies in the real world. Any body can be dented or deformed, even diamonds. Of course, you are all aware that it takes a bit more effort to deform a stone than a rubber band. And if you want to look at cases in which bodies barely deform at all, you can make your calculations much easier by just assuming they are rigid. There are various advantages to working with rigid bodies. They have fewer degrees of freedom, and it's easier to define forces. Let's look at a practical example of this. First, we take a look at a rigid square. This is a two-dimensional body. To start with, let's ask ourselves the question of how a body like this can move at all. If we assume that we remain in the two-dimensional plane and are dealing with a rigid body, we can determine that there are three options. We can move the square along the x-axis, to the left, or the right. And then we have the y-axis as well, of course. So, up and down. To finish off, we can rotate the square. Each individual option to move this body can be defined as a degree of freedom. In our case, we have three movement options, which gives us 3 degrees of freedom. By the way, this applies to all rigid bodies of this variety, regardless of shape. Triangle, circle, star, it doesn't matter. Now, we're going to look at the behavior of this body if we subject it to a certain force. Let's start by exerting a force from the top. We know that this body cannot be pressed together, as it is rigid. And this is a very special property of rigid bodies. Let's make the force's line of action complete. What's so special about all this? Well, we can move the force alongside this dotted line, but nothing changes for the body. It doesn't matter if the force is exerted on the top, the side, somewhere in the middle, or on the bottom edge of the body. Real bodies have different properties when exposed to all this, because various deformations occur depending on the force exerted. It's really convenient to just be able to move forces around. And the next example will help you understand just how exciting, yeah, really, this can be. Let's take as our example an equilateral triangle with a side length of 6. Now, let's unleash our forces on this triangle. Using the force shift, we can define the resulting force. To do so, we first draw lines along which individual forces are exerted, which looks something like this. Let's first define the partial result given by the red and yellow forces. We extend both forces along their lines of action, up to the point where they meet. Now, we can determine the force resulting from both these individual forces, which will then look like this. We repeat this step with the remaining forces in the same way, by extending the lines of both forces to their intersecting point and determining the result. And that's all, folks. We have reduced 3 individual forces to one single result. We demonstrated the graphical solution process here. It allows for very good results. But because your ruler will never be truly accurate, it also always leads to inaccuracies. The calculational procedure is better because it is much more accurate. However, we will save a calculation example for another video. Well, that wraps it up for today. Today, we took a closer look at the special properties of rigid bodies and their advantages. We know that forces that are exerted on rigid bodies can be extended along their lines of action. And we also know how to graphically define the resulting force from a number of force components. If you didn't quite manage to pull this off, you can have a look at our video with a practical 3-dimensional example as well. Well, for now, all that's left to say is, get cracking, you lovely bunch. Catch you on the flip side.